Good morning, everyone. This is Yufan Zhang in Yunich Research Center. Today, I will be discussing how my work in water management in cathode side of polymer electrolyte fuel cell accelerates the ongoing energy transition. And in particular, I will show that to get a correct oxygen transport distribution, we need to model the liquid saturation explicitly and model it in the whole cathode. To achieve low initial mobility, we use hydrogen as fuel. Good operation of fuel cell hinges on local reaction conditions. In particular, liquid water plays dual role. It builds proton pathway, but it blocks oxygen transport. As a strategy, we need to ensure an optimal water distribution, not only in the catalyst layer, but also in the diffusion medium. It is the coupling between the catalyst layer and diffusion medium that is matter. Have you seen this kind of polarization curve? At high current density, there is a drastic voltage drop, a signature of the limiting current behavior, also commonly referred as the knee shape. In order to avoid this knee shape and to further propose mitigation strategies, we need to first understand its cause. A common belief says that at high current density, excessive liquid water accumulates, leading to a flooding of the catalyst layer. However, theoretical analysis shows that this hypothesis is incorrect. If we maintain the oxygen pressure at the interface between catalyst layer and diffusion medium and increase the current density, there will be more water generated. And that will lead to a decrease of the reaction penetration depth. And that will only lead to a smooth decline of the voltage, following the law of the doubling of Lambda slope. So the knee shape can solely be attributed to the decrease of oxygen pressure at the GDL and CL interface. And that is the signature of the GDL flooding. To test this hypothesis, we have proposed a model to model the saturation distribution at the whole cathode. So in our model, oxygen and gas diffuses through the diffusion medium into the catalyst layer. Reaction produces water, part of the water vaporizes, the other part exits the cell in liquid form. Our model is one-dimensional, microhomogeneous, and endothermal. In particular, effective properties, saturation distribution, pressure and fluxes are all coordinate dependent. The saturation in our model is both a composition variable and a solution variable. It all starts with composition and structure of the porous medium. With the initial guess of saturation, we can calculate for the effective properties. And with transport equations and boundary conditions, we can calculate for the pressure and fluxes. With the help of water retention curve, we can calculate another saturation. We repeat this loop again and again until saturation converges. So in catalyst layer, we consider primary pools and secondary pools. We consider hydrophilic pools and hydrophobic pools. In the diffusion medium, the hydrophobic pool is 3 orders of magnitude larger than the catalyst layer. And this stark difference will lead to very different water retention curves of this two porous medium. And that will lead to very different saturation level in this two porous medium, and as we will discuss later. The saturation is calculated by the capillary equilibrium. At the gas and liquid interface, force balance maintained. The difference between liquid pressure and gas pressure is the capillary pressure. Laplace equation gives the capillary radius. In hydrophobic pools, all the pools larger than the capillary radius is filled with water, whereas in hydrophilic pools, all the smaller pools are filled with water. The saturation is simply an integral of all the process distribution over all the filled pools. Let's move on to the water retention curve. At the same capillary pressure, the saturation in the catalyst layer is very different from that in the DM. And the saturation of the diffusion medium is more sensitive to capillary pressure than that of the CL. So let's have a look at the effective properties. So here shown are 2 examples. On the left column, the diffusivity of these 2 media decreased with saturation, whereas in the right column, the permeability increased with saturation. Let's have a look at the transport equations. So for the left boundary between the membrane and the catalyst layer, we assume 0 flux boundary condition. And at the right boundary between the GDL and flow field, we fix the pressures. And at the middle interface between CL and DM, nothing is fixed. They are all self-consistently solved. So now we can close this loop by recalculating a saturation based on the structure-based water retention curve. So now let's have a look at the cell performance. At high current density, there's a drastic voltage drop, there's a knee shape. And if we analyze the saturation distribution across the whole cathode, we can identify two features. Firstly, saturation in the cathode layer does not rise much with current density. That is because at these four current densities, water invades all the hydrophilic pools, but almost no hydrophobic pools is invaded. And so this clearly shows that the knee shape is not the cause for the cause of the CL flooding, because until now the CL has not been flooded yet. The second feature is after reaching a critical current density, the saturation in GDL increases, and there is a formation of water layer that is a fully saturated layer. Let's rationalize this discontinuity. We know that the capillary pressure maintains continuity at the interface, but the water retention curves of these two medium are different. At low current density, the capillary pressure is low, the saturation of the GDL is still very low. However, once we increase the current density, the capillary pressure increases, and that leads to the GDL saturation reaching 1, whereas the saturation in CL remains relatively unchanged. Having known the saturation distribution, let's have a look at the diffusivity and oxygen pressure. The water layer causes an abrupt decrease of the diffusivity all the way to the residual diffusivity, and that decrease results in a decrease of the oxygen pressure at the interface. So indeed, our hypothesis is proven. So I hope I can convince you that to get a correct oxygen pressure distribution, we need to model the saturation explicitly and over the whole cathode. Okay, let's crack on and propose some mitigation strategies. We can tune the water retention curve by adjusting the process distribution and wettability of the GDL. We set basic parameters as what we shown in the last slide, and we vary one parameter while keeping the other fixed. Compared to the base case 1 has smaller pools, the PSD peak moves to the left. And for case 2, the contact angle is increased. So we can see that at the same capillary pressure, the saturation for the case 1 and case 2 is lower than that of the base case. So it seems that they may have better performance. And indeed, our model shows that the voltage does not drop until very high current densities for these two cases. And if you look at the overall potential, 0.45, the saturation distribution, there is an absence of water layer for case 1 and case 2. Therefore, having smaller hydrophobic pools and higher contact angle is beneficial. And interestingly, there already exists a porous media that has smaller hydrophobic pools and more larger contact angle. And that is the macroporous layer, the MPL. What if we introduce MPL into the catalyst layer and diffusion medium? And what if we replace the GDL with the MPL? Our model shows that if we fix the total thickness of the diffusion medium, introducing MPL is beneficial, and using MPL solely is even better. And this phenomenon has been observed by experimental studies several years ago by Chang Wang's group. We know that the MPL has smaller diffusivity compared to GDL at the certain saturation level. But in an operating fuel cell, these two media are not at the same saturation level. The saturation level is determined by their water retention curves. Because of smaller pools and higher contact angle, the more hydrophobic nature, MPL has a smaller saturation level compared to GDL when applied at the same capillary pressure. So if we combine these two plots, diffusivity versus saturation, and saturation versus capillary pressure, we arrive at this diffusivity versus capillary pressure plot. At small capillary pressure, GDL indeed has a larger diffusivity. But as soon as we increase the current density, we increase the capillary pressure, the saturation of GDL increases and the diffusivity of GDL decreases to residual values, whereas an MPL still have a very high diffusivity. So to sum up in this talk, we present a comprehensive water balance model for cathode side. It has a self-consistent treatment of saturation, effective properties, and local reaction conditions. We reach a problem at high current densities where the saturation have like water layer where the diffusivity and oxygen pressure decreases and initiate. We can utilize the water retention curve to propose mitigation strategies, including more hydrophobic GDL, GDL with smaller pores, and using NPL. These are my co-authors, and I want to thank them. And as a final note, I'm a final year PhD candidate looking for a postdoc position in theoretical chemistry. And this is my personal website. It shows my CV, my previous researches, and my ongoing research on electronic metal support interaction. Please feel free to drop by. Okay, in that, thank you very much for your attention.
Thank you. Thank you very much, Yufan, for this very interesting talk. I'm sure there are some questions and we also have a little bit of time.
Away from the mic. I tried to speak up, yeah, thank you for an interesting talk. So it wasn't quick, so one question. So if the GDL is fully saturated, how can you still increase the current density? How does the oxygen reach the catalyst layer?
Yes, this is a very good question. Thank you for your question. So as you see here, if the GDL is fully saturated, the diffusivity reaches its residual diffusivity. And there's a limiting current behavior, so the current density cannot increase a lot. So you see there's a almost vertical drop. But it depends on which residual diffusivity we consider in our model. So theoretically, the residual diffusivity of oxygen in water is 2 times 10 to the order minus 9 meters squared per second. But as we know, our model is one-dimensional. In reality, it is 2-dimensional. So there will be some area of GDL fully saturated and some area that is not fully saturated. So if we consider this real reality in our model, we increase the residual diffusivity from 2 to the order minus 9 to 2 to the order minus 8. So it still gives me some increase of the current density. So it is not a strictly vertical line.
Okay, thank you.
Thank you.
Further questions from the audience?
Follow up on this comment, wouldn't it be then better to apply a different model instead of hacking on some physics-based diffusion constants to get the model matching experimental data?
Yes, I think this is a trade-off. For a different model, it may increase the complexity and blur the physical picture. But I totally agree with you that we need to come up with some updated model to account for the reality. And yes, thank you very much.
Thanks. Actually, I'd also like to add a quick question. So in the literature, it's often also discussed that in addition to a bulk diffusion resistance, you also have an interfacial mass transport resistance at the surface of the platinum. And there's also this typical 1 by roughness factor dependency that also some people showed in previous talks. And I think that this would change your change of the penetration depth and would also cause some contribution to limiting current. Did you also consider that as an explanation?
This is a very sharp observation. So this local resistance of the oxygen transport can be incorporated by adding a agglomerated model into our macrohomogeneous framework. And yes, that would be a possible way for updated model. Thank you.
Thank you very much, and let's join me to thank the speaker again.
And our final presentation